to go. So what I want to do today, and I do apologize for getting started late, I want to talk about the various ways in which we can store data and store information. Let's see if I can get that right. And store information inside of a computer. So at this point in time, we've talked about how we digitize stuff, but we've never actually talked about how do we store things. How do we store those ones and zeros? So we have a couple of different ways. For example, on a hard disk drive, that's stored with magnetics. And we're storing with a minus is like storing a 0, and a plus is like storing a 1. All right? So we're talking about polarity, right? Magnetism. A negative, 0, a plus 1. Other ways in which we can do it is with light. So when we think of compact discs, DVDs, Blu-rays, etc., what we're looking there is the intensity of the light as it comes in. So for example, a pit would be a 0. And that's what we call them. We call them pits and lands. And a land would be a 1. All right? A pit and a land. So if a laser strikes a pit, it would reflect back and determine a lower level of light being reflected back. So that would be a 0. Reflects back at a higher intensity. It says, well, that's a 1. And then finally, we can use electricity. And with electricity, we represent it as 5 volts is going to be a 1, and 0 volts is going to be a 0. We're talking about low voltage stuff, so low voltage rail. 5 volts is a 1, 0 volts is a 0. Now, when we first started coming up with computers, we had the ENIAC, and the ENIAC was made of a whole bunch of vacuum tubes. And vacuum tubes enabled us to be able to represent ones and zeros, to be able to process things. The problem with that is they were really hot. The vacuum tubes are really hot. Think of an incandescent bulb and how hot the incandescent bulbs got. And there were thousands of these vacuum tubes in the first ENIAC. So we literally had somebody walking around 40 hours a week replacing vacuum tubes on ENIAC and the other computers of that era, pre-transistors. Then finally somebody came along with this idea of a transistor. And then a transistor has a semiconductor material. And there's multiple parts to this particular transistor. We got the base, which we'll also refer to as input. We have the emitter, which we'll also refer to as ground. Up at the top here, we're going to have the collector. Now, the collector is always going to have 5 volts applied to it. It's always going to have plus 5 volts applied to that. And then off that, we can have a little line here, and we're going to call that output. And then inside, if you look at like diagrams, inside our transistor is going to have some different wires that's going to enable this semiconducting property that semiconductors have, that transistors have. What's up? Electricity over here. We have electricity, we have emitter, right? So to understand how a transistor works, to understand how our modern world works, we need to know some basics about electricity. I'll give everybody a minute to to keep taking down notes. So we need to know some basics about electricity and what it flows through. First, what's the difference between an insulator and a conductor? Okay, can we say electrons? All right. So a conductor enables us to be able to transmit electrons over the material. So conductor is, give me an example of a conductor. Give me an example of a conductor. No. A wire. What kind of wire? What's a wire made of? Copper. Give me another example. Gold. Give me another example. It could be. It's not the best conductor, but it can be. That's the opposite. That's going to be a what? Rubber's going to be a what? If it's not a conductor, it's an insulator. So rubber's an insulator. Other conductors, almost any of the metals out there, silver, so on and so forth. All right? An insulator, rubber, plastics, wood, so on and so forth. Poor conductors, right, cannot transmit electrons easily. All right? So a semiconductor acts as both. It acts as both a conductor and it acts as an insulator. All right? Now, the other things that we need to understand about this is the properties, the basic properties of electricity. The first is this. Electricity always likes to get to some place. Anybody ever seen lightning before? That's electricity. Where is it trying to always get? Where are those lightning bolts trying to get? What are they striking? Which is connected to what? The ground. So electricity always likes to get to the ground. And when I say the ground, literally the earth. It wants to get as quickly as it possibly can to ground. So that's the one property of electricity. It always likes to get to ground. And the other is this. It always likes to take the path of least resistance. Think of it as like water. Have you ever seen water coming down a hill? If there's a rock in the way, it takes the path of least resistance. It doesn't go through the rock, it goes around the rock. So electricity is the same way. When it encounters any type of an insulator, any resistance to its typical flow, it's going to find another path to get to ground. And that's where our semiconductor comes into play here. When there is 0 volts applied to my semiconducting material, it acts as an insulator. Okay? It acts as an insulator. It's a path of great resistance. So this 5 volts that I have up here being applied to the collector, it won't travel through my semiconductor. It'll go through this wire to seek ground another way. So if in my input I put a 0 in, I get 5 volts out. So if I put a 1 in, I get a 0 out. All right? Now, as soon as I put a current voltage to my base, to my input, so I change it from 0 volts. I did have multiple colors. I don't know where they went. Oh, here we go. So as soon as I change my input, my 0 volts to 5 volts, my semiconducting material now does what? It conducts. It acts as a conductor. This is a miraculous material. Our whole modern society is built around this one teeny tiny device. So now it becomes a conductor. And when it becomes a conductor, all 5 volts that I put in here, where does electricity like to go? To ground. So it all travels down to ground down here. The 5 volts that I have up here being applied to my collector all come down and go to ground. So if all 5 volts from here are going to ground, all 5 volts from here are going to ground, what's coming out? Nothing. 0 volts is coming out at that point in time. That is the basic properties of a transistor. Our entire modern world is founded on this. If you're looking at your screen, you're looking at hundreds of thousands of transistors. Transistors that are telling the pixel to turn on or turn off, or what level of brightness for RGB it should be. Your processors inside of your smartphone contains billions of these. They're the building blocks of all hardware. All right? And notice how I said that. They're building blocks. Just like the ones and zeros are the building blocks of ASCII or JPEG or your movies, these are the building blocks of all modern digital equipment. Do you go around manipulating the ones and zeros when you program? Do you physically manipulate those? No. They're building blocks. You use code to do that. Same thing here. We don't actually worry, because there's billions of these inside of modern devices, we don't actually worry about manipulating the individual transistors. We abstract the transistors out and we start talking about these things called logic gates. So all the logic gates that we're going to cover in this particular class abstract out the transistor configuration which lies underneath of them. Yep. Yep. We're getting there, only we're not going to do that one yet. Be patient. So in the book, there's 3 different logic gates that are covered. I'm going to give you 6 between today and Friday, and I want to introduce you to a new piece of software. All right? So the first logic gate that I'm going to introduce to you is called a NOT gate. As I give you information about the different gates, about the logic gates, I'm going to give you the diagram. So if we looked at a schematic of a computer, you could see the different gates that are being used in that device. I'm also going to give you the Boolean logic for it. So there's this guy named George Boolean who created a whole field of mathematics called Boolean algebra, which enables us to be able to create these different diagrams. All of the anding and oring that we do in programming is founded around this. And then the last thing I want to do is give you the truth table. The truth table tells us all of the states and what the output will be for a gate or a combination circuit. We know, because they're finite state machines, depending on an input, what the output will be every single time with exacting accuracy. So the first thing I want to give you is the input for my diagram of a NOT gate. Now, this little square box that I have, we're going to call this an interactive input. This is the diagram for a NOT gate. It's a triangle with a circle on the end. And that little circle, anytime you see that, it always means not. I have an X over here, which is going to be on an LED. My A is my label for my input. My X is my label for my output. So we can commonly refer to the different parts of my diagram. So there's the diagram for a NOT gate. It has one input of A and an output of X. The Boolean for this says X equals A not. Now, if you have taken a digital electronics class, a digital logics class elsewhere, and they used a bar to represent not, that's called bar notation, You can use bar notation. I don't have any problem with that. You've had that before? So two different ways to represent the not, the little apostrophe after it or a bar over it. So this reads x equals a not. That's how the Boolean reads this. So diagram, Boolean. It's the Boolean equation. And the last thing is the truth table. Now the truth table has two parts to it. It has the inputs and the outputs. Now in this case, I have one input A and I have one output X. If I have one input, you're about to log out. I don't want anybody to log out of your machines because we're going to switch to software in a minute. So pay attention, make sure you don't get logged off accidentally. If I have one input, how many different states can my circuit take? How many are there? It's an exact number. I got one input. 2. Why 2? Because it can only be a 0 or a 1. We're in base 2. We're in binary. Each input can either be on or off. That's it. So I'm going to start at 0, and I'm going to put the other state, which is 1. This particular gate has one input. So 2 states. 2 to the number of inputs. 2 to the 1 is 2. Now, the properties of a NOT gate are whatever I put in, I get the opposite out. Therefore, we refer to a NOT gate as an inverter. So it's a NOT gate, but it's also called an inverter. Whatever I put in, I get the opposite out. So if I put a 0 in, I get the opposite out, I get a 1. I put a 1 in, I get the opposite out, I get a 0. So this is the only time they're going to ask you this. What does the configuration of the transistors look like for a NOT gate? Andrew? What's that? Absolutely. So a NOT gate is one single transistor. Now that's the only time that I'm going to ask you this and have you to think about that. It's a logical representation of the physical transistors underneath. That's what all of our gates are going to do. In this case, it's easy to see. But as we get into AND gates and OR gates and exclusive OR gates and exclusive NOR gates, it's difficult to understand what all the transistor arrangement is underneath. And I don't expect for you to know it. Because as computer scientists, all we need to know is how this stuff works. So when we want to hook up a sensor to a Raspberry Pi or another device, we know how to signal it appropriately. We know what the different states for that sensor or for that LED will be and how to hook them up. All right. So the next thing that I'll have here is I'll do an AND. Now I want to help you through the AND gate. So the AND gate, again, I want to have 2 inputs on this one. I have an A input and a B input. And you'll see in a few minutes why I keep drawing a square around those. I'm going to start calling those an interactive input. And then my diagram kind of looks like this, kind of looks like a capital D. And then I want to draw a wire from my interactive input into my gate. This is an AND gate, to be clear. I could have more than 2 inputs. This is a 2-input AND gate. But I could have a 3-input AND gate or a 4-input AND gate. We're just going to represent 2-input AND gates. And then I'm going to have an output to an LED, and I'm going to label that LED X. So this is my output LED. These are my input. Everybody's good? No problemo? I'll give you the Boolean. So I gave you the diagram. If I brought in a schematic you could look at it and you could identify an AND gate, you could identify a NOT gate. You'd be able to look at it and say, oh, that's what that is. The Boolean is X equals A and B. Remember, we're in Boolean's world. This is Boolean algebra. So it's not A times B. That dot is an AND. So it's A and B. We read it that way. X equals A and B. All right. The last thing that we do is...
Really?
She's crazy. Siri is insane, man. You heard her. Next thing we do is the truth table. All right. So how many inputs do I have? I got 2. So I'm going to write A and B into my table. On my left is my inputs, and on my right is my outputs. I got one output of X. So far we've only dealt with 1 or 2 inputs and 1 output. But you need to understand the screen that you look at in front of you, however many pixels are on that screen, how many physical pixels there are, that's how many outputs there are. Actually, it's more than that. It's 3 outputs per LED. All right? 1 for red, 1 for green, 1 for blue. So however many pixels there are, which is like, I don't know, a million or so, 1920 by 1080, times 3, that's how many outputs there are to that screen, each screen. In here I only have 2 inputs. So if I have 2 inputs and each input can hold a state, either a 0 or a 1, how many different states can my overall gate hold? 4. 2, because it's base 2, to the 2. That 2, all right, 2, that's my base 2. Each input can only hold 1 of 2 states. It's either on or it's off. That's it, right? And the other 2, that represents number of inputs. So 2 to the 2 equals 4. So what are the different states? We know this, right? We start at 0, so we go 0, 0, and we count until we have 4 different states represented. 0, 0, 0, 1, 1, 0, and 1, 1. The property of an AND gate. All right? Now, again, we could draw out the transistors. We could get a bunch of transistors, configure them in an AND gate, and see what the properties are by applying, 0 volt, 0 volt, 0 volt, 1 volt, 1 volt, 0 volt. I'm sorry, not 1 volt, 5 volts. 5 volts, 5 volts, and see what the output would be. That's where this comes from. Properties of an AND gate say both must be true, so there must be 5 volts applied to both of the inputs for the output to be true. So 0, 0 yields a 0, 0, 1 yields a 0, 1, 0 yields a 0, and 1, 1 yields a 1. We refer to this as ANDing. How many people had Cisco before? Cisco people, anybody? Do you remember when you ANDed the IP address to the subnet mask to determine the network, right? That's what we're doing here. This is called ANDing. We're ANDing those bits together. And the only time it's going to yield a 1 is if both of the bits or all of the inputs are 1. Everybody with me? Questions? Thoughts? Okay, at this point, I want to show you a piece of software. So hopefully you're logged in. Everybody's logged in? All right. So the piece of software that I'm going to give you, it's going to show up on your desktop in 1 second here. Give me just a minute. It's going to be in the LAN. Is everybody logged in? It doesn't feel like everybody's logged in. All right. Maybe they are now. All right. So I'm going to give you a piece of software. It's going to be in the LAN school files. And it's going to be called digitalworks.zip. So I got to send it to you, and then I'll show you what to do with it. Don't do anything with it until I show you, okay? Okay, so everybody should have it at this point. Should be on your desktop in a folder called LAN School Files. It's a zip folder called DigitalWorks. This is also on Canvas under Files. All right, so you can download this and use this. Now, what I want you to do is you have that zip file. I want you to right-click on it. And we have 7-zip. If you don't have 7-zip, you just say extract. Extract would show up. So we're going to 7-zip extract to DigitalWorks. And then a new folder should show up. Neighbors help neighbors if you don't get that. All right? You got to extract the file. What I don't want to happen is when I assign a project with DigitalWorks, you not extract the file, spend 2 or 3 hours on your project, go to save it and can't save it. That's because you didn't extract it. And that's exactly what will happen. Anybody not where we're at right now? Is everybody good? Speak now, because I'm about to move on. Everybody good? All right, inside of DigitalWorks, there's a little file called digital.exe. Double click on that, and we get this. Now, full disclosure, this program is about 23 years old. But it's free, as opposed to a modern piece of software that would cost me about $30,000. We're not computer engineering. We're computer science. All right? I don't need to show you all of the big stuff. That one, double click. Okay, now double click. There you go. There you go. I don't need all of that stuff, so I'm not going to pay for that. This is just, remember, it's about software. That's what we do. It's about software. Hooking up a Raspberry Pi, hooking up an Arduino, so we understand the signaling processes that are going on. That's all we need to know. However, because it's so old, the user interface isn't the best. So we're going to take a minute and we're going to review this. Across the top, we got the basics. They call these macros. Your file is called a macro. So we can say new macro, which is going to produce a new breadboard for us. We can open an old macro. We can save, so on and so forth. Under edit, this is the only way to do copy and paste. You can't use Control-C and Control-V. Under circuit, you got the basics: run, stop, pause, step. You can set up a clock speed as well. That is exactly what it sounds like. Clock speed of a CPU, clock speed of your different buses, so on and so forth. Under view, you can change that. Under tools, so on and so forth. The top toolbar right here are all of these files, right? The next toolbar down is the most important. This toolbar, the middle toolbar, and the bottom toolbar are the most important. These, you can't see my screen, right? Okay. All right. The middle toolbar and the bottom toolbar are the most important. The middle toolbar are all the different gates that we're going to talk about. So as we hover over each one of these, it'll tell us what the gate is. So for example, here's a NOT gate, and here's an AND gate. As we come over RS and JK flip-flops, that's what your memory is made up of inside of your computer. Your RAM, it's JK and RS flip-flops. All right. On over, we have a macro, embedded macro. That's how we can build larger circuits. This software is sophisticated. You could build a whole virtual computer if you wanted to do that. All right? I don't recommend it. Not with this software. We have an interactive input. That's going to enable us to toggle between 0 and 1. And then we also have an LED. And then the last thing is the wiring tool. The last toolbar down, we have the play button, we have the stop button, the pause button, we have the object selector button, and the interaction selector. All right? So let's take this AND gate and put it onto our breadboard. So you're going to find the AND gate, you're going to click on it, and you're going to click on your breadboard. That's what this is down here. You're going to click on your breadboard and drop it in there. The next thing we need is two interactive inputs. So I click on the interactive input and I drop it onto my breadboard. I select another interactive input and I drop it on my breadboard. I also need an LED. So I'm going to grab an LED and I want to drop it on my breadboard. Notice that I'm giving plenty of distance between my interactive inputs, my gate, my AND gate, and my LED. To get fine grain control of these, you can select an object and then use your cursor keys to move it around. All right. We can also label these, so we can right click and we can say text. I want to label this as A. I want to right click, I want to say text. I want to label this as B to match what I have on the board. I'm going to right click on my LED and I want to call that X. When I'm in my LED, notice that I can change the color of my LED to red, green, yellow, or blue. I'm going to leave mine red. I will pause. Do not start wiring this up. Let me teach you the tool. Give me just 3 or 4 minutes to teach you the tool, then you can start doing your own thing. Save a lot of heartache. Neighbors help neighbors if you're having problems. Otherwise, I want to grab the wiring tool. Now listen, the wiring tool is finicky. When you grab it, you don't even really know that you have it. Your cursor doesn't change. So you go to what you want to wire. It's got to be interactive input to input and output to LED. I can't do an output to an interactive input, and I can't do an interactive input well, maybe I could do that to an LED, but you don't want to do that. So you're going to grab it, and I want to draw a wire between my A input and the lead on my A gate, or my AND gate. So I got to wait till it says wire, and I click. Now, one of the things you can do is you can pin this to the breadboard. So you click, and you can pin it to the breadboard so you can run your wires nice and neat. And you can actually do that with a physical breadboard, and I'll bring in a physical breadboard on Monday to show you some of this stuff. However, it's not connected until you hover over that LED, that lead, and it says wire. Now it's connected. My wire is now connected. I'm going to do the same thing for my B. Connected. Then my output to my LED. Now once I've done that, those of you that are done, you click on Run, you select your interaction tool, and now a 0, 0 produces a 0. A 0, 1 should produce a 0. A 1, 0 produces a 0. And a 1, 1 produces a 1. I'll walk around, see if anybody needs help. Neighbors help neighbors if necessary. Got it? You good? Getting there? All right, man. Good job. It's good to experiment, good to play with. Don't forget, this is free. It's under Canvas, under Files. So now you get to wire it up. Wiring tool now. All the way at the end. There you go. Click on Run. You got to click on Run, and then you need to get the interaction tool. The little finger is your interaction tool. So click on the interaction tool. No. That's the object selector. There you go. Perfect. There you go. Now you click and run. Yeah, click run. And then click on this. It should be okay. 1, 1. Again. Something may not be connected appropriately. Look, I see a little macro tag in there. I'm not sure what that is. Looks like everybody got it. All right. So this is what I want to do. I've given you a NOT gate. I've given you an AND gate. I want to give you the OR gate, and then we'll wrap all of this up on Friday. So I'm going to give you an OR gate. Input of A and B. So I got my OR gate, input of A or B. It's going to go out to my actual OR gate. It kind of looks like this with an LED of X. The Boolean for this reads X equals A or B. The plus is an OR. Remember that. We're in Boolean's world. The next thing we're going to do is we're going to set up our truth table, and I want you to fill in the truth table. Now, you should know the properties of an OR. You know how to evaluate OR and. So you should know what it will be, but I want you to put it into DigitalWorks and fill this in. 2 inputs. Each input can have one of 2 states. So 0, 0, 4 different states for this. 0, 1, 1, 0, 1, 1. You fill in what the output should be. But do it with DigitalWorks. Plug it into DigitalWorks. Experiment with DigitalWorks. Once you're done that, once you have what the properties of my truth table are, and you've done it in DigitalWorks, class is over. On Friday, we're going to cover the last 3 gates, which will be a NAND gate, a NOR gate, and an exclusive OR gate. So if you want to do those, you can. Those are the ones we're going to cover. Then we're going to do combination circuits. Understand how to create a truth table for a combination circuit. And hopefully we'll wrap it up on Friday. Wrap up chapter 4. That's my goal. Questions? All right. Well, I'll walk around and see if anybody needs help. Otherwise, we're done.